Okay, so far what we've looked at is backtracking search. There's another algorithm for solving CSPs. This is called iterative improvement or local search. And the way this works is that you start with a near solution and then iteratively improve it. So if we could think about this from the point of view of this dice puzzle, for example, what we would do is we just start by sort of randomly putting the cubes into some configuration, and then we look around and say, okay, well, there's some constraints violated here. Okay, so this face is fine, there's no problem there, but this face has two reds. Right, so maybe I'll take one of those red cubes and tweak it. I'll rotate this one cube so that I've got a white there. So now these two faces are okay. But then I rotate it again and say, okay, well, the problem is there's two whites here, so maybe I'll try to solve that by rotating one of these cubes, and then I'm sort of okay, but now we've got two greens. So how would we apply that approach to some of these problems? Well, let's have a look at the n queens puzzle. Okay, let's look at 4 queens instead of 8 queens. So let's just randomly put 4 queens on the board and see what happens. Okay, so how many constraints are violated here? Well, that's attacking that, that's attacking that, that's attacking that, that's attacking that. So there's 5 constraints that are violated. So we say, okay, h equals 5. H is the cost of that particular configuration. So then we ask ourselves, okay, I'm going to move 1 queen and try to make it so that fewer constraints are violated. So the way we normally do this is I pick a queen at random. I don't consider all queens, I just randomly pick one. And then I say, okay, well, I've got 3 other options. I'm going to try to pick the one that improves my situation as much as possible. So if I bring the queen down here, I would still have 4 violations. If I bring it here, I would still have 5 violations. If I move it up here, then I've improved my situation. This isn't attacking anything anymore, so I've gone from 5 violations to 2, so that's the best move that I can make. So I've improved my situation, and then luckily here, if I pick this queen and move it down, then I'm actually violating no constraints. Okay, so this is a different way of approaching the problem. So with backtracking search, you're only assigning one variable at a time, the others are totally unassigned. Here you're assigned all the variables, but then you're changing them one at a time. Now this is sometimes called iterative improvement or local search. Sometimes it's called hill climbing, and in this case it's called hill climbing by min conflicts. Now let's think about why this is called hill climbing. So what you imagine is you're moving around in some high dimensional conceptual space, and there's some hill you're trying to climb, and you try to get to the top of that hill by taking one step at a time. And you imagine, it's called local search because I imagine that I can't see the big picture. It's a heavy fog, I can't see more than a few meters in either direction, but in this situation I'm trying to just take one step at a time and try to improve my situation. So we think about it as this kind of conceptual landscape. Here we've drawn it in just 2 dimensions, but you think of it as a multi-dimensional landscape. And sometimes it's called descent, sometimes it's called climbing. If it's hill climbing, we think about trying to climb to the highest possible objective function, but if we phrase it in terms of the number of constraints that are violated, then we're actually trying to minimize that. Right? So then we'd have to look at this picture upside down, and we're trying to climb into a valley rather than up to a peak. In most parts of the world, when you go walking in the mountains, you actually start at a low level and try to climb up to the top of a mountain and then climb down again, right? But when you walk in the Blue Mountains, it's actually, you start out on a ridge and then you walk down into the valleys and come up again, right? So you're actually trying to reach the lowest point and then come up again. And if you're hiking with children, you have to make sure they don't get too tired because they're going to have to walk uphill on the way back and so on. So this, if we think about it as minimizing the conflicts, then we're actually, it's climbing down the valleys in the Blue Mountains rather than climbing up the peak. But the principle is still the same. Okay, but it's a multi-dimensional space. So if it's 8 queens, I've got 8 different directions in which I can move. And, you know, again, like my vision is very impaired. I just think, okay, I'm going to try to move from here to here. And all I can tell whether I went up or down. So we assume I'm trying to climb up. I take a step, and if I've gone up, then that's good. I sort of move the other foot, and this is my new position. If I try something and I'm actually going down, then I reject that choice and I just come back to where I am. So you may actually sort of try multiple choices to try to see which direction is going to take you up as fast as possible. So here we've chosen this particular queen, and you can see how many constraints are going to be violated for each of those positions that I can move it to, and I pick one that has the fewest, so up there there's only one constraint, and then I randomly pick another queen, and this one has, down here is 0 constraints, so I move it down here. Right, so this is called hill climbing by min conflicts. Now it turns out that for this n queens problem, this kind of local search is much better than backtracking search. In fact, you can do 10 million queens very rapidly just by doing this min conflicts. Now that's not to say that local search is always better than backtracking search. It really depends very much from one task to another. But for this particular task, local search turns out to be very good. And there's an interesting principle here that the difficulty of the task depends on the number of constraints, and this is true in general for almost all constraint satisfaction problems, that there's this kind of spike in the middle. If there's very few constraints, then it's usually easy to solve the task. Because remember, we don't have to find all possible solutions, we just need to find one. Right? So if there aren't many constraints, then I've got a lot of freedom to choose the variable assignments, and it's very easy to find a solution. Now similarly, if there's a very large number of constraints, the problem also becomes easy, perhaps paradoxically. The reason is those extra constraints guide the search very effectively. And when I do my backtracking search, branches are going to get pruned off very quickly because the constraints are going to give me very few options at each stage. And usually there's some critical ratio in the middle where the problem becomes very hard. There's sort of just enough constraints to make the thing really, really difficult. And this is a general principle that you see in almost all CSPs, and whatever method you use to solve them, whether you're trying to use local search or backtracking search, you still see the same phenomenon. Now, one of the problems with this local search, sometimes it can get stuck in a local maximum. So this is not the case with the n queens problem, but it may be the case in some other problems. So let's think again about this dice problem. I got to a situation here where I've got very few constraints violated, right? So that face is good, that face is good, that face is good. So my only constraint is that there are 2 greens here. So there's really only one violation. In fact, this is as close as I could possibly be. But most likely, I can try all possible rotations of this cube, keep leaving the others fixed. I can try all possible rotations of this cube, leaving the others fixed. But I may very well find that there's no way of manipulating one cube to improve my situation. It may be that in order to get to the, so this is kind of this is called a local maximum, right? It only violates one constraint, but I'm going to have to change several cubes in order to get to the global maximum. So I'm kind of stuck here in this local maximum, and I'm going to have to make my situation worse in order to get up to that global maximum, right? So this is a potential problem with this hill climbing search, that I would actually get stuck here. I try these combinations, and then there's nothing that's the end, right? So we want to have a variation of hill climbing that can get us out of these local minima. That variation is called simulated annealing, but I think at this point we're probably due for a 5-minute break. So when we come back, I'll tell you about simulated annealing, and we'll also give you our little potted history of artificial intelligence. So going back to this simulated annealing, so this is a kind of stochastic version of hill climbing. So the scenario is still the same, right? So this is my current situation, and the number of constraints that are violated in my current situation I'm going to call H0, and then I pick a variable, I look at the options for that variable, and the best possible option for changing that variable will violate a number of constraints called H1. Okay? So this is H0, this is H1, and I'm trying to decide, should I make the step to the H1 or should I stay where I am? Right? Now with standard hill climbing, I only make the change if the number of constraints in the new place is less than the original one. So if H1 is less than H0, then I make the switch. If it isn't, then I don't make the switch. Actually, there's another little implementation issue here. What happens if H1 and H2 are equal? Should I switch or not? Yes, I should switch, because it's been shown that a lot of these constraint satisfaction problems may have large flat areas where the number of violations is the same. So it's actually, if you can find a new place that has the same number of violations, it's actually good to make the switch, because you may have to sort of wander around randomly over that plateau before you get to a new place where there's some gradient you can climb up to the next level. But in any case, there's kind of an aside. So with hill climbing, if H1 was strictly greater than H0, you definitely wouldn't make the switch, right? Now the way simulated annealing works is the following. Okay, so if the new place is preferable to the old place, I definitely make the switch. No question. Now, if H1 is bigger than H0, in other words, the new place violates more constraints, I might still make the step. So I actually calculate this number, e to the minus H1 minus H0 over t, and this gives me a number between 0 and 1, and I generate a random number between 0 and 1. If the random number I generated is less than this, then I make the switch, otherwise I don't. Okay. Now, you might look at this and think, well, this is quite bizarre, where did these numbers come from? Okay, well, first of all, let's have a look at what happens as t changes. So, first of all, what happens if t equals 0? Now, e to the minus something divided by 0, that's e to the minus infinity. E to the minus infinity is 0. So if when t becomes 0, this algorithm reduces to ordinary hill climbing, right? So if the temperature is 0, I'm back to my hill climbing. I won't make any step unless it improves my situation. Now what happens as t goes to infinity? Well, dividing by infinity is the same as multiplying by 0. So e to the minus 0 is what? 1. Right? So what this says is, I should always make, if t goes to infinity, then it's saying I should always make the switch regardless of what h0 and h1 are. Right? So you get these two extremes. When t goes to infinity, you're actually looking at total random search. I'm just randomly jumping around all over the place, not caring about the fitness. When t goes to 0, I'm strictly adhering to the hill climbing, and when t is some number in between, then it's a mixture. It's saying, okay, well, I'm more likely, there's always some probability that I'll make the switch, but I'm more likely to switch to positions which are good than positions which are bad. Sorry, you had a question up there.
Why did it says no randomness? You're always switching no matter what. H1, H0 are.
If t was infinity, you wouldn't need a random number generator in that case.
I think you're saying that the idea is that like you would always change, but the point of t being infinity becoming totally random is that you just move to whatever state, it doesn't matter. So whenever you find a new state, you change to it. So that's how it's a random search in that sense.
That's right.
I was going to say, I think it's already, t is just a random number that you just put in, right?
Ah, t. Okay, so what normally happens is, strictly speaking, if t is a fixed number, then this is usually called the metropolis algorithm. When we use the word annealing, it usually refers to a situation where we actually change t over time as the algorithm progresses. So the idea of this is that t starts out at a high value, and then gradually over time it decreases to a low value. Now, again, this may look ad hoc to you. How on earth did anyone come up with this algorithm? But there's actually a very important physical intuition behind this algorithm to do with statistical mechanics and magnetism. Right? Now, a ferromagnet is a magnet that's made out of what material? Iron, right? So it's a block of iron which is magnetized. But I could alternatively have a block of iron which is not magnetized. And the two things look very similar, both of them are iron, right? What is the difference between a magnet and just simply a block of iron?
Two different poles.
Two different what?
Poles.
Two different poles, that's right. So the atoms in the iron are arranged in this kind of rectangular lattice, and each atom has a spin and it can be either up or down. If all or most of the atoms are in the same direction, then it's a magnet. Otherwise it is. But if they're just sort of randomly dispersed, then it's not a magnet. Now, let's say I start out with that iron bar that's not magnetized and I want to make it into a magnet. How would I do it?
Get another magnet.
Get another magnet. Yeah, I could get a bigger magnet and let's
strike it along a bit.
Yeah.
Sorry?
You rub it along the length of the piece of iron, right?
Get another magnet and rub it along the length. Yeah, I think that would work.
You can melt the iron down and then allow it to cool within a magnetic field as well.
That's right. Yeah, that's the answer I'm looking for, right? So you heat the iron up to a very high temperature and you put it into a magnetic field and then you cool it very, very slowly. And that's this word annealing actually refers to that process. It means heating something up and then cooling it very, very slowly. And when we say putting it in a magnetic field, in nature it could be the Earth's magnetic field that it's in. Okay? And the rate at which the temperature comes down is called the annealing schedule. And so if you cool it too fast, it won't become magnetized, but if you cool it very, very slowly, it will become magnetized. Right? Now, there's this thing called the Ising model of ferromagnetism, and basically it describes this thing as a constraint satisfaction problem. So you've got millions and billions of little atoms in this lattice, and so each atom is a variable, and it can have two values either up or down. And the constraints are that it's a bit like a map colouring problem, right? If colouring this map with two colours, the constraints are, in this case, we want in the map colouring problem, we wanted neighbouring countries to have different colours. In this case, we actually want neighbouring atoms to have the same spin. So these two atoms don't violate a constraint. That's what we want. These two violate a constraint because their spin is different. And the same with these two. So you can actually go through and figure out how many constraints are violated. And there are two different configurations which have the minimum that violate no constraints. One where all the spins are up, another where all the spins are down. Now in practice, you can never make an absolutely perfect magnet. There's always going to be some that are pointing the wrong way. But the idea is you have to have a sufficient number of them that are pointing in the right direction. Now, believe it or not, what happens when that iron is heated up and then cooled down again actually follows this equation, right? There's slight differences in this. In the real situation, we don't have this extra condition that if H1 is H2, you definitely change. And in the physical situation, there's an extra constant in here called Boltzmann's constant, which we don't worry about that when we're doing it computationally. So there's a couple of slight differences, but basically this algorithm has been designed to mimic what happens in nature when you make a ferromagnet. So there's actually some physical intuition behind this. And when we talk about the annealing schedule, that's the place we want to end up, right, the global minimum. So when you start with a very high temperature, you're just kind of wandering around randomly all over the place, right? And then you reduce the temperature very, very slowly, and hopefully what will happen is you'll spend more time in this region than you would in that region, you know, because it's bigger somehow. And then as you slowly cool down, eventually you hope to end up at that global maximum. That's kind of the idea of what's going on in this case. Whereas, so if you cool it very, very slowly, this thing will happen nicely, that you'll just smoothly move into that global optimum. If you cool it too fast, you'll get stuck in a local optimum. Right? It sounds like, I mean, it's just a hand-waving argument, but if you implement this and try it out on some problems, you'll find that it does actually work that way. Okay, so in summary, there's a lot of interest in constraint satisfaction problems for real-world applications. The standard simple algorithm is backtracking, which is depth-first search with one variable assigned per node. By certain heuristics to tell us the variable and value ordering, we can speed up the search significantly. Forward checking helps by detecting failure early. Hill climbing by min conflicts often effective in practice, like in the N-Queens problem. And if you get stuck in local optima, you can often escape with simulated annealing. And yeah, which methods are best? Well, it actually varies from one task to another. Sometimes local search is better, sometimes backtracking is better, sometimes forward checking helps you, sometimes arc consistency helps you, sometimes it doesn't. You really, over the years, just got to develop an intuition about this, or ultimately implement two different approaches and test to see which one is faster. Any questions about this?